Hello everyone and welcome to Robot Operating System version 2 Jazzy Jalisco tutorials. In this ROS2 tutorial, we explain how to model a mobile robot from scratch in ROS2 and Gazebo, and we explain how to write a Python code, shown over here, that controls the robot motion. Over here, you can see the Gazebo simulation of the mobile robot. In this video tutorial, we have modeled a robot with a differential drive control mechanism. However, everything explained in this video tutorial applies to robots with different actuation mechanisms. Here is the Python code that's used to control the robot motion. The idea is relatively simple. Over here, we create a message of the type twist. A twist message contains control commands for linear and angular velocities. We select the linear velocity and the angular velocity, and then over here in this while loop we publish this message. This message is being sent to the Gazebo simulation, and in this particular case the robot describes a circular trajectory. Everything explained in this video tutorial can easily be generalized to other types of trajectories. You can also modify our code in order to include a sensor and then even implement a feedback control algorithm, or even an algorithm that's more complex such as model predictive control or something similar. Here is a brief overview of what you will learn in this video tutorial. First of all, you will learn how to create a ROS2 package from scratch. Then you will learn how to write this robot.zacro XML file that implements the robot model and that defines the robot mass and moments of inertia. Then you will learn how to write this robot.gazebo file that implements the gazebo properties of the simulation as well as the differential drive plugin for controlling the robot. Then you will learn how to write this YAML file that bridges ROS2 and Gazebo topics such that we can send information, or better to say messages, from ROS2 to Gazebo. Then you will learn how to write this Python launch file that will start all the nodes, and then you will learn how to write this Python file that controls the Gazebo simulation. In addition to this, we have created two tutorials, or better to say two manuals, that thoroughly explain all the steps that you need to perform in this video tutorial. Here is the first manual. It is 8-page long. And here is the second manual that thoroughly explains the robot model, namely it shows the robot geometrical description, then it explains how the coordinate frames are being placed and assigned, and also this tutorial explains the moments of inertia of the robot body as well as of the wheels and the caster link. Links to all these files, that is, link to these two manual files and all the source code, will be given in the description below this video as well as in the comment section below this video. The video tutorial that you're currently watching is self-contained. This means that we will explain every file and every single line of code. However, in order to save time, we will quickly go over some steps. Mainly, we will quickly go over modeling of a differential drive robot. We will explain every code line, however, this will be done relatively quickly. If you want to know more about modeling of differential drive robots, we have created an almost 2-hour-long tutorial shown over here that thoroughly explains how to model differential drive robot. A link to that tutorial will be given in the description below. Consequently, it might be a good idea to first watch this video tutorial over here and then to watch the video tutorial that you're currently watching. Let's start with modeling. This video tutorial is designed for people who are completely new to ROS2 and Linux Ubuntu. Consequently, we will spend a significant amount of time explaining the basic concepts. Let's start with the prerequisites. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL, since you might have issues displaying graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. Let's verify that you have the correct version of Linux Ubuntu. To do that, open a terminal. Click here, search for terminal, click here, and then in the terminal you just need to write a single command. That command is lsb release-a, and over here you should see your Linux Ubuntu version. Next, you need to have ROS2 Jazzy Jalisco installed on your system. If you don't have ROS2 Jazzy Jalisco, then go to my YouTube page and search install ROS2 Jazzy on Linux Ubuntu, and there are several tutorials. After you do that, let's verify that you have properly installed the operating system. First of all, run this command. This command will list the content of this standard installation folder for ROS2 Jazzy. And if you see something like this, then most likely you have properly installed ROS2 Jazzy Jalisco. However, in order to properly verify everything, let's try to execute, or better to say source, this script called setup.bash. If you don't see an error, that's a first good sign. And then finally print this environment variable, and if you see Jazzy, then you have installed Jazzy Jalisco on your system and you can continue watching this video tutorial. The next step is to install the necessary packages. Before you install any package, you need to do two things. First of all, you need to source the ROS2 environment as we did, and secondly, you need to run these two commands. Sudo, and let me just copy it like this, such that we can save some time. Here are the two commands. First command is sudo apt-get update. This command will update the local package list on your system, and the second command is sudo apt-get upgrade. This command will upgrade all the packages on your system, and then after that enter your super user password and wait. Depending on how often you execute this command, the execution might last several seconds, as in my case, or it might even last several minutes. The next step is to install Gazebo Harmonic. To install Gazebo Harmonic, you need to execute this command. As you can see, Gazebo is already installed on my system. However, in your case, it might take even several minutes to install Gazebo. The next step is to verify Gazebo installation. Here, you need to source the environment, or better to say, to execute the setup.bash file once again. And then let's try to run Gazebo simulation. However, before we do that, let's list the content of Gazebo installation folder, or better to say, let's retrieve the path. Here it is. This means that Gazebo is actually installed, and let's try to run Gazebo simulation by running this command. And you will see this window, and let's try to run one of the simulations. For example, let's click over here and click on run. Let's just wait for a while since it might take a while to load this simulation. To run this simulation, let's click over here, and then you can try to move the robot by changing the things over here. That is by changing the joint position. Okay, let's continue further. You can close the Gazebo simulation window. The next step is to install the necessary packages. So let's start with this package. Then let's install this package. Then let's install this package. And then finally let's install this package. These are the packages that are necessary to execute our simulation. Next, let's verify that packages are installed. To do that, you can run this command. This command will list all the packages, and then it will search for a package containing GZ in its name. And you can see all Gazebo packages over here. For us, the most important package is ROS GZ Bridge and There is also another one, ROS2 simulation. Okay, the next step is to create the workspace folder and the package. For that purpose, I'm going to close this terminal and I'm going to start from scratch. So click here and open a new terminal. And again, whenever you open a terminal and you want to play with ROS2 commands, you need to source the environment. That is, you need to execute this command. Let's create the workspace folder. First of all, make sure that you're in the home folder, and then create inside of the home folder two folders. The first folder, called ws_mobile, is our workspace folder, and inside of that folder we are going to create the source folder. Next, let's navigate to our source folder, and inside of this folder we need to create our empty package. To create an empty package, or better to say to create a package template, we need to execute this command. The command is ROS2 package create. Then we need to specify what is the build type we want to use. Since we are going to write a Python code, we are going to write amend Python, and then finally we give the name to our package. In our case, it's mobile robot. And if you press enter, you can see over here that several files and folders are created. If you type ls, you will see a new folder. This is our package folder. So let's navigate to this folder. And over here, you will see several files and folders. Let's create 3 additional folders inside of this folder. For that purpose, we are going to use this command. We are going to create the launch folder, model folder, and the parameters folder. And then if we list the content of this folder, we can see everything. Let's briefly explain what are these folders. The launch folder is the folder that will contain the Python launch file for running the nodes. We will write that file later on. The mobile robot folder, that is the folder that has the same name as the name of our package, will contain the Python source code for controlling the robot. The model folder will contain Zacro, or better to say XML files for modeling the robot geometry. Package XML is a configuration file. Parameters folder is a folder that will contain a file that will bridge ROS2 and Gazebo packages, or better to say topics. Resource folder is a folder for resources. We will not use it in this video tutorial. Setup.configuration is another configuration file that's automatically being populated by the command that's used to create the package, and setup.py is another configuration file that we will edit later on. Test is the test folder. So let's start with implementation of our model. To do that, navigate to the model folder, and inside of this folder we need to create 2 files. In this video tutorial, I'm going to use Visual Studio Code to create the files. If you don't have Visual Studio Code on your system, then you can use any editor, any basic text editor, or you can follow tutorials on my YouTube page that will teach you how to install Visual Studio Code on Linux Ubuntu. Simply go to the YouTube page and search for install Visual Studio Code on Linux Ubuntu. Let me start Visual Studio Code by running this command. Here it is. To define the robot geometry and dynamics properties, we need to create a file whose name is robot.zacro. Here, click on File, then New File, and then I'm going to paste this name. And then I'm going to save it in the model folder. Here it is. To save time, I'm simply going to paste the content of the file. Here's the file. I will copy it and then I will paste it over here. And let's explain this file line by line. To explain this file, we are going to use the sketch of the robot geometry shown over here. So let's start from the beginning. Any XML file that defines the robot geometry should start with this tag. Then, this is how we write comments. We start the comment tag like this and we end it like this, and this is a comment as well as this line, this line, this line, until line number 9. Line number 9 defines the robot tag. We start the robot tag over here, and at the end of the file we have to end the robot tag. Let me show you that over here. Don't worry, this file looks like it has 271 lines, however, maybe even more than half of the lines are comments. So let's go back at the top and let's proceed further. First of all, over here we are specifying the robot name. The robot name is differential drive robot, and then you have this standard description. So just type this thing over here. The first step is to define the geometry and constants. Here we are using the Zacro macro language that will enable us to define macros that are later on used in the code. Namely, in many formulas, we are going to use pi. Instead of writing every time 3.14159 or something similar, we are just going to write pi const. The same applies to the robot dimension. Instead of every time writing the robot length of 0.1 or 0.6, we are just going to write a. Consequently, at the beginning of this file, we define these constants as well as the parameters. Here you can see the graphical representation of the robot, and let's go over the specific variables. A is the length of the robot body. Here is A. Then we have B. Well, what is B? B is the height. And C, defined over here, is the width. This is the robot body. Then we need to define wheel dimensions. Wheel has the length of D and the radius of R. And we define it over here. Here is the radius R, and here's the wheel width. Good. Next, we need to define S1, S2, S3, and S4. Here's how they're defined. And note over here that they're the functions of A, B, C, R, and D. And this is the power of using macros. That is, we can write formulas later on. And if you want to change some parameters, you're going to simply change the parameters at the top of the file. So let's see what is S1. Okay. S1 is shown over here. S1 is the distance of the center of the robot body with respect to the horizontal plane. What is S2? Let's find S2. S2 is the distance between C2 and C5, or C4 to be more precise. C5 and C4 are center points of the wheel 1 link and wheel 2 link. That is the centers of the wheel. That is S2 is the horizontal distance between the center of the robot and the center of two wheels. Then we have S3. S3 is the distance between C2 and C3. The point C3 is the center of the caster wheel. And then we have S4. You can also see S4 over here. Okay, let's continue further. Next, we need to define mass and moments of inertia of the robot body. First of all, we need to define the density. Again, we are using the variable. The density is 2700. This is approximately the density of aluminum. Then we define the wheel material density. Here it is. And caster material density. Then we need to define the mass of the wheel, caster, and the robot body. To define these masses, we are going to use famous formula saying that the mass is volume multiplying the density. So let's find the formulas. Here they are. First of all, we need to compute the mass of the robot body. Here is the volume of the robot body, namely, since the robot body is the box, its volume is A multiplying B multiplying C, and the mass is density multiplying the volume. And over here you can see the implementation. Simply the density multiplying A, B, and C. Then let's go further. How about the wheel? What is the volume of the wheel? Here is the formula. It's pi radius squared multiplying the height. And here is the implementation. And then to get the mass, we simply multiply the volume by the density and we get this value. Then let's talk about the caster. Here is the formula for the caster. Caster is a sphere. Here is the volume of the sphere. And over here you can see computation of the mass. Simply the volume of the sphere multiplying the density, and that's it. Next, we need to define the moments of inertia of the robot. Over here, you can see the formulas for the moment of inertia of the robot body. You can see Ix, Iy, and Iz, and over here you can see their implementation in the Zacro file. Next, let's define the moments of inertia of the wheel. First of all, let's find the formulas. Here's the first formula. Then, Ix is implemented over here. Let me now just expand this so you can see it. Ix I will simply denote by I wheel. I'm doing this because Ix and Iy for the wheel are the same, and I'm going to simply denote them by I wheel. Similarly, here is Iy, and here is the implementation, and here is Iz. Okay, and then let's talk about the sphere. The three moments of inertia of the sphere are equal. This is because sphere is symmetric with respect to x, y, and z axes. And then we can see over here that we only have a single implementation. I will call it simply as icaster, and it's equal to Ix, Iy, and Iz. Next, we need to define the tensor of inertia, or better to say, we need to define the matrix of inertia. First of all, we need to start with the robot body. We start this macro, we end the macro, we start the inertial section, we end the inertial section. This is a simple comment, as you can see over here. Then we need to define the origin of our coordinate system. Let me show you this on the graph. If we go all the way up, and if you look at the geometry, robot body is displaced with respect to the horizontal plane for S1, and consequently here we will have 0, 0, S1, and this defines the point C2. Next, we need to specify the mass. The mass is denoted by M1, and over here we need to specify the moments of inertia. This is actually a matrix of inertia. We only have 6 values over here since the matrix is 3 by 3 and it's symmetric. So this is Ix, Iy, and Iz, and the products of the moments of inertia, that is Ixy, Ixz, Iyz, are equal to 0. Okay, so this is the macro for the moment of inertia of robot body. We do the same thing for caster. Here, again, we start the macro, we end the macro, we define the origin, and here comes one very important thing. Here we have a rotation of the coordinate system for our inertia of the wheel, and coordinate system is rotated for pi over 2, and later on you can see them in Gazebo simulation. Consequently, we have pi over 2, we have the mass, and then over here we define the moments of inertia. Here they are, and that's it. And we do the same thing for the sphere. Here it is, equivalent. We start the macro, we end the macro, we define the inertia, and that's it. Next, we need to include additional file. Namely, in order to simulate the model in Gazebo, we need to specify parameters for the Gazebo simulation. Consequently, we will include this file, robot.gazebo. However, this file is still not being created, and we will create it in the sequel. However, this file will be stored in the model folder, and this find mobile robot will simply return the absolute path of our base package. Okay, next we need to define links and joins. For that purpose, let's again look into the robot sketch. Here it is. This configuration consists of several links. Namely, every geometrical shape is modeled as a link in URDF. We have the body link representing the robot body. Then we have 2 wheel links called wheel1 underscore link and wheel2 underscore link. And then we have the third caster link. Between the links, we have joints. That is, joints are connecting links. In this case, we are going to have several joints. First of all, in order to simulate the model in Gazebo, we need to define a fictitious or a dummy link, which I will call base footprint. Then the joint name is the first basically join. It's body link join. It's going to be fixed. Then we need to specify the parent link. The parent link is actually the base footprint, and the child link is the body link, which is the body of our robot. Okay, now that we've done that, that is after we define the first link and first joint, we can proceed further. Next, we need to define the body link of the robot. The link name is body link. Over here we specify the visual representation. Let's look back into our sketch. Let's see what is the visual representation. It's a box, as you can see over here, with the dimensions A, B, and C, and we simply specify the dimensions over here. Next, we need to define the displacement and orientation of the geometric center of the link with respect to the link frame origin. We can see that the center is displaced over here, and the distance is S1, and consequently over here we type this. And we end the visual representation. Next, we need to define the collision box of our robot. Collision tag or collision box is simply a copy of the visual representation. Collision enables Gazebo to detect collision between objects and to provide you, for example, bouncing and similar dynamics effects. And finally, we need to include inertia section. Inertia section is a macro that's defined over here at the top. And that's our body link of the robot. Next, we need to define the back right wheel of the robot and the joint. First of all, we need to specify the joint name. The joint name is wheel 1 joint. The type is continuous. Continuous means that we can continuously rotate this joint. The parent link is the body link. The child link is wheel 1 link. That is, it's over here, and we need to define the displacement of the origin. It's minus S2, minus S4, and R. So let's see. Minus S2, minus S4, and R. And that's it. Then we need to define the axis of rotation. We are going to rotate it around the local y-axis, and then we need to specify the limit effort. Limit effort is the maximum torque that can be applied to the wheel, and over here is the maximum velocity. Next, we need to define dynamics damping and friction, and that's our joint. Similarly, we define wheel 1 link. We start the link, we end the link, we create a visual representation. Geometry is a cylinder with a length of d and radius of r. We define rotation of the coordinate system over here, and we end visual. Collision is simply the copy of visual, and then we add the macro that defines the inertia matrix of the wheel. If you go all the way up, you will find this section over here that defines the inertia wheel. And now you can see the power of macros. You can simply type inertia wheel, and the parser will place it over here. This makes the code more readable. Next, we need to define the wheel 2 joint. Here's the wheel 2, and we need to define the joint. Its parent link is body link, its child link is wheel 2 link, its origin is displaced like this. Its axis is y local axis of rotation. Here's the limit effort, here's the damping and friction. And then finally we need to define the wheel 2 link. It's a cylinder with a length of d, a radius of r. Its coordinate system is rotated with respect to roll axis. And then we have the collision properties over here, and then we add the inertia section, which is defined previously. And finally, we are left with a caster wheel. We define the joint. It's a caster joint. The type is fixed. That is, we are fixing the caster, and caster can only slide. Here we are defining the parent link, the child link, the origin, and that's it. And then finally we define the caster link. It's a sphere with the radius of r, and over here we don't have any displacement and rotational coordinate systems. Here's the collision section, and over here we have inertia section, and that's it. And we end robot, and that's the final geometrical description of our robot. And we can continue further with additional gazebo properties. Note over here that on line 111 we have included the file called robot gazebo. So let's create this file. I'm going to simply copy the name of the file, then I will click File, New File, and I will create the file and store it in a model folder. And here, to save time, I'm going to simply copy and paste the content of this file. This file defines additional properties that are necessary to simulate the model in Gazebo. Again, this is an XML file, so we start the file like this. This is the comment section, and we start robot, and then we end robot at the end, here at the line 80. Then we need to define this gazebo reference for the body link, that is, for the body of the robot. We need to define mu1 and mu2 parameters, and then we need to specify the material color. In this case, I'm using red color. We do the same thing for the wheel 1 link, wheel 2 link, and for the caster link. Here, mu1 and mu2 are actually friction coefficients. Okay. Now that you do that, that is, once you define mu1 and mu2 and the colors for every link of the robot, you need to define the plugin. This section is the comment, and over here we define the plugin. The plugin is used to control the robot. Namely, we're going to send velocity commands, that is the desired linear and angular velocity, and Gazebo has a plugin that will transfer these velocities into the proper motion of the wheel, such that the center of the robot body moves with the desired velocity and angular velocity. For that purpose, we used the plugin called Gazebo Sim Differential Drive, and over here we are specifying the name, and then we end the plugin. Over here we need to specify the parameters of the plugin. We need to specify the right joint, the left joint. These are the wheel joints. Then we need to define the kinematics. This is the wheel separation and the wheel diameter. Then we need to define the limits, such as the max linear acceleration. And then here comes a very important part. We need to define the topics. The topics for the command velocity will be command velocity. The topic for TF is given over here. The topic for odometry is given over here. The frame ID is odometry. Child frame ID is the base footprint. And the odometry publisher is given over here. We are going to publish odometry with 30 Hertz. That is 30 messages per second. And that's the end of the plugin. And over here we have the joint state publisher plugin, such that we can publish the joint states if we need them. Again, you're using this plugin. Here is the name. Then we have to specify the topic. The topic is the standard joint states. And then we need to specify wheel 1 joint and wheel 2 joint. And that's the end of the plugin and end of the Gazebo file. Good. Let's save this file and let's continue further. The next step is to define the file that creates a bridge between ROS2 and Gazebo. Namely, we are going to use ROS2 topics to publish command velocities to Gazebo. And for that purpose, we need to define this bridge underscore parameters file. So I will copy this file name, then I will click on File. Oops, not new window, I don't want that. File. Oops, again, error. File, new file. And I will call the file as bridge underscore parameters, save it inside of the parameters folder. And to save time, I'm going to copy and paste the content of the file. Here it is. Oops, I didn't copy it well. Let me do it again. As mentioned previously, this file or this parameters file will bridge ROS2 and Gazebo topics. Consequently, you're going to define ROS topic name, Gazebo topic name, ROS type name, Gazebo type name, and direction. Let's look into this clock topic. Clock is a standard ROS2 topic. Equivalent in Gazebo is clock. The ROS type name, that is the type of messages that are being sent through clock, are given over here, and Gazebo type name is given over here, and this is the direction. The direction is from Gazebo to ROS, and that's it. If you want to submit from ROS to Gazebo, here it will be written ROS2 Jazzy. Okay, then we start with joint states, and equivalently we specify how the bridge should be performed. Then we do the same thing for odometry. Note over here that the standard ROS topic for odometry is nav messages odometry. Then we do the same thing for TF, that is for the coordinate transforms. And finally, here is the most important topic that we are going to use. It is command velocity. Note the name CMD velocity. This is the name that we will use in our Python file. Here is the Gazebo topic name. Here is the ROS type name. Obviously, we are going to send twists. You will see later on the structure of twists. Gazebo type name and direction, this is very important, is from ROS to Gazebo. So let's save this file and let's continue further. The next step is to create a file that will launch the nodes. For that purpose, we need to create a file whose name is given over here. So let me copy this name. Let me go to File, New File, then specify this name, and save this file in the launch folder. Let's create a file, and again, to save time, I'm simply going to copy and paste the content of the launch file. Let me do this, and let me paste it over here. Again, first time I copy, for some reason it's not working. The second time it will work. Let's look at the big picture and explain the purpose of this file. The purpose of this file is to start several nodes at the same time. First of all, we are going to start Gazebo simulation, then we are going to start the bridge, and then we are going to start an additional node, as you will see later on over here. We are going to start the robot state publisher. And this will be started, that is, all these three nodes will be started with a single command line. First of all, we need to import the necessary libraries, modules, and packages. Inside of this function, we define how nodes are being started. First of all, we need to define the robot Zacro name. This name has to match the robot name in the Zacro file. If you open the Zacro file, at the top you have the robot name. The robot name is differential drive robot, and you can see the name over here. Next, we need to specify the name of the package. It's mobile robot. Then we need to specify the relative path of our robot.zacro file with respect to the base package folder. Namely, if we now go back to command prompt or terminal, you can see that robot.zacro is inside of the model folder, so its relative path is given over here. And this relative path is defined with respect to the base workspace folder. Okay, then we need to get the absolute path of the corresponding file. We simply use this function get package share directory, name of the package. This command will return the absolute path of our package, and then we add the relative path. Then we read the robot description over here. And then we need to specify the path of the Gazebo launch file. Namely, in addition to our launch file that we are using, we are going to use the standard Gazebo launch file. And for that purpose, we are going to retrieve the absolute path of that file. It is inside of the package directory of ROS Jazzy sim. Then there is a folder launch, and here is the launch file. This is simply the path to the Gazebo standard launch file, which we will use later on. And then we define how the thing should be started. Then, first of all, we specify the path to the launch file for Gazebo, and we specify the launch argument. So here are the launch arguments. We are going to use the empty world. SDF is the file for the world. That is, we are going to place in the empty environment. And then we specify additional things such as on-exit shutdown, true, etc. Then we need to start the Gazebo simulation node. We need to specify how we are going to start. The package is ROS Gazebo simulation. Executable is create. Then we need to pass to this node our Zacro file. Note over here that this is the absolute, this is actually the name, right? Not the path. And then over here we are specifying or passing the robot description. This is actually the description of our robot, and the output will be screen. Simple as that. Then we need to specify the additional properties. We need to specify the robot state publisher node, package, executable, output, and then over here we are specifying our robot description. Here it is, and we are using the simulation time. And then here's a very important node setting that we need to properly define. We are going to use a bridge node to bridge ROS2 and Gazebo topics. First of all, we need to specify the parameters we are going to use. That is, over here we are saying that we are going to use parameters defined in the bridge parameters file. And then over here is our node. We are using ROS Gazebo bridge. The executable is parameter bridge. Here are the arguments, and here we are passing the bridge parameters, and the output is screen. Then we create a launch description, and then we add things. We add Gazebo launch, spawn model node Gazebo, node robot state publisher, and our bridge over here, and we simply return the launch description. Good, let's save this file and let's continue. The next step is to implement the Python file for controlling the simulation. For that purpose, let's create a new file. Click on File, then click on New File, and let's call the file as test.py. And then let's save the file inside of the mobile robot folder inside of our base workspace package folder. Note over here that this folder has the same name as the base package folder, and you can identify that folder by searching for init.py file. Namely, that folder should contain this file. Okay, and again, to save time, let's copy and paste the content of the file. Let me do it twice. Let's paste it over here. Okay, let's explain the purpose of this file. The purpose of this file is to control the simulation. That is, we are going to control the robot motion from this Python code. How to do that? Well, at the beginning of the file, you need to import RCLPY. RCLPY is the ROS2 client library for Python that is included with any standard installation of ROS2 distribution. RCLPY provides the standard application programming interface for using ROS2 with Python. Then we need to import the node class. Those of you who are not familiar with ROS, everything in a ROS environment is object-oriented. That is, nodes, which are actually programs, are embedded inside of the classes, and consequently we need to import class. Then we need to import twist messages or twist class. So what is the twist? Twist is the message type we want to send from this code to our Gazebo simulation. Twist is a data structure containing components of the linear and angular velocity vectors that are used to control the 2D mobile robot. Okay, these messages are sent through the topic called command velocity. And note over here that this command velocity is the same name as the name that you used in the bridge file. That is, we are using the ROS topic name command velocity, and this topic is bridged to the Gazebo topic name command velocity. Gazebo is going to receive through this topic command velocities, and then Gazebo is going to use this plugin to transform these velocities into the motion of the wheels. Okay, then we need to specify the rate of our messages. Here we are going to send messages every 2, or basically 2 messages every second. Here's our main function, which is relatively simple. Before using the RCLPY API, we must initialize it by using init. Then here we instantiate our message. Then we fill in the fields, namely the twist has 2 fields. It has a linear velocity field and it has an angular velocity field. These are actually vectors. Here we are specifying the linear velocity vector. We are only moving in the x direction. Basically, x direction is the axis associated with the robot and fixed with the robot motion. That is, as the robot moves, the x-axis is moving. That's the body axis of the robot, and this axis is always along the length of the robot body. And here we are specifying 4 meters per second. Y and z components of the velocity are 0, and here is the angular velocity. Here we are only having the component of the angular velocity that is perpendicular to the robot plane. And note over here again that x, y, and z axes are the body axis of the robot. Here we are creating a node. Then we are creating a publisher such that we can submit messages. We are submitting the messages of the type twist over the topic called command velocity, and over here we specify the buffer size. Then we create the rate object. The rate object will make sure that the messages are being sent with the desired rate, in our case 2 messages per second, and here is the while loop for controlling the robot. First of all, we are printing the message sending control message. Then we are publishing the message of the type control, actually of the type twist, and the name of the message is control velocity. Then we are spinning the node once. This means that the publisher will send the message, and over here we are posing the code such that we are sending 2 messages per second. Finally, if a user presses Ctrl+C, this while loop will end. We need to destroy node and we shut down everything, and this is the standard part such that the main function is being started if we start this code directly from the terminal. Next, we need to edit the configuration file such that we can correctly build our package. Click on File, then click on Open File, and let's go to the base package folder and open package.xml. Over here, after test dependencies, we need to add several lines. And here they are. Let me copy them. And let me explain these lines thoroughly. So what's happening over here? Namely, our package depends on standard ROS2 packages. And we need to specify these dependencies. First of all, our package should depend on joint state publisher, then the robot state publisher, then we have these ROS Gazebo packages, ROS Gazebo, ROS Gazebo Sim, and ROS Gazebo Bridge. Note over here that some of these packages are actually used either in this test.py file, such as RCLPY or geometry messages, or they're being used in the launch file over here. Keep in mind that. Then we have Zacro. We are using Zacro to define our Zacro model description. Then we are using RCLPY and geometry messages inside of the test.py file. And these are the dependencies. Let's save this file and let's continue further. Next, we need to edit the setup.py file. First of all, click on File, Open File, then go back to the base package folder and open setup.py. First of all, we need to create the entry points. So what are the entry points? Note over here that test.py is a source file. We need to define executable for this file. That is, we need to define the entry point. That is, we need to specify how this file is executed. And here we need to add these lines. Let me just copy them and let's explain them over here. Let's align everything nicely. So here, let's see what's happening. First of all, we need to specify the entry point. Here, the entry point, or the name of the file that will be used to start the test.py, will be publisher. That is, this is the name that we are going to use. Then we need to specify over here the package name. The package name is mobile robot. Then we need to specify the name of the file. The name of the file is test.py. Here you just need to specify test, and what we need to specify is the function that will be executed. The function is main. Once you put everything together, you will obtain this line. Consequently, once we type ROS2 run, name of the package, publisher, this thing will happen. We will look inside of the mobile robot package, we will look inside of the test.py file, and we will execute the main function. Simple as that. Next, we need to tell to our ROS2 build system that there are important files being placed in the folders we just created. Namely, if you go back and if you look into the structure of the package folder, you can see that we created launch, model, and parameters folders. These are the folders that are being created in addition to default folders, and the default folders are test, resource, and mobile robot. Since we additionally created 3 additional folders, we need to tell to ROS2 system to look for files and folders inside of these new folders. So let's learn how to specify this. First of all, at the top of the file, you need to add these additional imports, import os and import glob. Then you need to do the following. Here, you need to add these 3 lines. Let me copy them. And these lines should be added inside of this data files list. This is how they should be added. Let me do this, and let's explain what's happening. Here we are simply saying that we want to add launch folder, share, package name, launch, this is basically the path, and then look for file in folders, that is for all the file and folders inside of launch. We do the same thing for the model folder, and we do the same thing for the parameters folder, and that's it. Let's save this and let's continue. What is important to keep in mind that the code that we will start, its name is publisher. So let's save this and let's continue further. Save setup, save package, save test, save gazebo, save bridge, robot.gazebo, robot.zacro, and let's continue. The next step is to build the package. For that purpose, let's go to the base workspace folder, and keep in mind that you always need to be in the base workspace folder when you build the package, and inside of this folder we need to build the package by running colcon build. However, before running this command, let's install a program called ROS2. ROS2 is used to check for the dependencies. First of all, you can install it by running this command over here. So let's initialize it by running this command, and then let's update it. And then let's run this command to verify that all the dependencies are successfully installed. If they are, you should see something like this. And let's build our package. To build the package, simply run this command. The command is colcon build. You are selecting the package called mobile robot, and let's see what will happen. There are no errors, which is a first good sign. The next step is to run the gazebo simulation. To do that, open a new terminal and then run this command. Note over here that this command will source or execute setup.bash file inside of the created package. So run this command and then run this command to run our Gazebo model launch.py file, which will start the Gazebo simulation. And let's see what will happen. Here it is. Perfect. The next step is to run our code. For that purpose, you need to open a new terminal, and in the new terminal, you need to repeat the procedure. First of all, you need to source the setup configuration file from the build package, and then you need to run the executable. You simply need to type ROS2 run, the name of the package and the name of the executable. Note over here that this executable is actually defined in entry points. Here it is. And that's it. And let's run this, and then you can see we are sending control messages, and if you open Gazebo simulation, you will see that your robot will move and the robot will describe a circular trajectory. The circular trajectory is the consequence of the fact that inside of the test.py file you have specified linear, constant velocity and constant angular velocity, and know that these are the constant velocities in the body coordinate systems. Okay, that's all for today, and thanks for watching.